The Cramer-Rao bound deals with the variance of unknown parameters. To start with, we have a parameter which is unknown but non-random. So we are not talking about random parameters. Of course, we start with some data, which is observations. So based on the data, we have an unbiased estimator for theta. Unbiased means the expected value of the estimator is theta. So this is the condition. So then the Cramer-Rao, remember, this being an estimator, it has its own variance. So the question is, by being clever, you can, of course, we want the estimator with the lowest variance. And if you are clever to some extent, you can get multiple estimators with the different variances. Naturally, variance being a positive number, one of them will be the smallest. So you can pick up that to be the better estimator among whatever you have. But the question is, how far can you keep going? So the theorem says that there is a bound. In other words, you cannot keep improving the estimator. And I'm going to prove the result. So the result is true under the so-called regularity conditions. So the regularity conditions, as you can see, one is that the derivative of the integral of the density function and the integral and the derivative can be flipped. So you cannot do this for all density functions. Wherever you can flip it, remember, area under the density function is 1, so this is 0. That's obvious, right? So the whole point is you can bring this derivative outside. If you can bring it, you need to bring it out. So that's regularity condition 1. Condition 2 is you should be able to do this on Tx, where Tx is any estimator for theta. In fact, an unbiased estimator for theta. In other words, Tx is our theta hat x. Okay. So we could write this as Tx also. Maybe I'll keep writing Tx. It is. So I'm going to show that for any unbiased estimator, the variance is lower bounded. It has two expressions. I'll come to this. So let me start with this expression. So remember, by definition, if Tx is unbiased, this is just the definition of Tx, right? This is what we mean by unbiased estimator. The estimator multiplied by the density function, right? This is the expected value of Tx. So this I can write it also as theta f x comma theta dx. So consequently, I can put it together, and the limits are from wherever they are. Okay. So this I can write it as Now I am going to use the regularity conditions and take the derivative, which you can do here also. So if I take remember, this is just the same as this expression. So you can see the derivative here goes inside, right? So using remember, split this as you have the two integrals. Using condition number 1, the derivative here will go here, and using condition number 2, the derivative will go there. Right? So we can take the derivative here. So this is the same as this derivative comes here. So let me just save some one line and write it from here. Okay. So that's equal to 0. And now if you use a partial derivative, this is going to be so the derivative of this quantity, which is minus 1 multiplied by fx of equal to or plus integral Tx minus theta df x of theta d theta. So I'm going to write this, I'm going to take this thing to the other side and write this as tx minus theta because the area under the density function is 1. Okay, now if you look at, to simplify this further, so if you take the derivative of logarithm of f of x comma theta d theta using the logarithm expression, this is 1 over f of x comma theta multiplied by df x comma theta d theta. So d derivative of f with respect to theta is, by cross multiplying this here, you get this expression. So I'm going to use this expression here. So I get tx minus theta, and instead of derivative of f, I'm going to write f multiplied by d log f over d theta. So I can write this as f of x comma theta d log f of x comma theta dx equal to 1. This dx could be in multiple integrals depending on the number of data sets. So this is a vector, of course. The integral also is multiple integral. Now, to save a line, I'm going to write this as in this fashion, because f is a non-negative quantity. So I can write this as so I'll rewrite it here. So this integral is now tx minus theta So I get this this expression, and let me write this to be ax, and let me write this to be bx. And I want to use Cauchy-Schwarz, so to see whether, so what I have is, I'll write it here, or let me go and take it here. So I'm going to square this, and that is still true. Okay. Anybody remembers what is Cauchy-Schwarz? Integral of integral ax dx dx squared is less than or equal to what? All right, so that's the result. So this is the same as integral a squared x integral b squared x. And when will you have equality here?
When they are scalar matrices.
What?
When they are scalar matrices.
Yeah, right. When ax is of the form k multiplied by bx. So we'll use that also. So look here. This expression is equal to 1. I wrote it like this. So let me use Cauchy-Schwarz. So I'm going to write this squared multiplied, this is greater than 1. That's what it is. So I'm just going to substitute it. So I get tx minus theta squared. And now you can see why I took the square root. So when I square it, you get this dx multiplied by, this is a squared, and b squared you can see is square of that. So that is d log f of x comma theta d theta squared f of x comma theta is greater than or equal to 1, because the 1 is here. You can see that this is greater than or equal to 1. Okay. But look here, this is what? This is some function multiplied by the density function. So this is expected value of this quantity, but that's the variance. This is the variance. So that's the variance of Tx. And look at here, this is some quantity, so I'm going to write whatever it is. So that's d log f of x comma theta d theta the whole squared. Expected value is greater than or equal to 1. So from here, I can bring this quantity down and I get this result. 1 over expected value of d log f of x comma theta derivative squared, which is the first expression here. So notice this is a positive quantity because whatever it is we are squaring and taking the expected value. So this is a positive quantity. Now there is also a second form. So to derive the second form, so let me take the derivative of this expression. It's a simple manipulation here. So that's a fundamental lower bound for the specific problem. It says that the variance, you cannot improve. There is no point in trying. If your variance is already equal to this, you are done. You cannot improve it beyond this. So that's in that sense, it's a lower case. Of course, then the best case is when you have reached a situation where the variance is equal to this. So if you want equality here, we need this equality. So I'll go to in a minute. Let me just finish. Let's take this expression. And I'm going to take integral on both the sides. Look at here, it's a simple manipulation. And now using the regularity condition, this goes outside, right? This derivative goes outside. So the integral of the density function is 1. Derivative of 1 is 0. So this answer is 0. If you do the integral, it is going to be 0. Okay. Now let me take the derivative of this integral. So again, I'm going to use the regularity condition. So the derivative goes inside. So what I'm going to write is the derivative of that quantity, which is f multiplied by d log f by d theta. This is 0 because it is 0 here. Now this derivative, by regularity condition, this goes, remember, this goes inside. And then I get the two expressions. I get df by d theta, d log f by d theta. And then I get another expression is plus integral f multiplied by the second derivative of log f. And this is equal to 0. Now what I'm going to do is for df by d theta as before, remember we had an expression before, df by d theta, this is the expression we had before. So for df by theta, I'm going to substitute it here for this expression here. So from there I get, remember I'm only going to concentrate here. So this is, you can see it's f multiplied by this quantity. So I get f of x comma theta multiplied by d log f of x comma theta d theta squared plus d squared log f x comma theta d theta squared multiplied by f of x comma theta is 0 dx. But look here, this is the one expression is expected value of d log f x comma theta d theta squared. So this expression is equal to this expression, and the other expression is expected value of the second derivative. So we get this expression. So look at what it says. Expected value of the square of the first derivative of the logarithm of the density function is the same as minus expected value of the second derivative of the logarithm of the density function. So in other words, this denominator is minus of this expected value of this. So you can use either one of the two expressions to compute the Cramer-Rao bound. So this is the Cramer-Rao bound. And before I finish this, I just want to discuss what happens in the equality case. So remember, as you said, as somebody said there, if you have equality, then your estimator is the best estimator because it has the lowest possible variance. Equality means variance of Tx equal to the Cramer-Rao bound, right? So if I call this whole thing to be sigma squared CR, this whole thing, right? Either this or that, then that means this estimator has the lowest possible variance. Among all unbiased estimators, right? Remember, we are only talking about unbiased estimators. And as you said, the condition for equality is this one. The one function is, remember, these are the two functions. So where are the two functions? So the quantity which we had before. So I'll write the AX and BX. D log f of x comma theta d theta multiplied by square root of equal to some constant multiplied by this was your A, this was your B. So A is some constant multiplied by, let me write it be A, some constant, right? And remember, this is common, so I can get rid of this. So the condition actually turns out to be this one. So when you have such an estimator, you call this estimator to be, if it meets the Cramer-Rao bound, then this is supposed to be, we call it to be the efficient estimator. So efficient estimator is when the unbiased estimator meets the Cramer-Rao bound. Now look here, there is actually a surprising result. So this is the condition for efficient estimator. But on the other hand, remember, condition for, what is the condition for ML estimator? Anyone? What is the condition for ML estimator? Maximum likelihood estimator is what? You take the likelihood function and look for its peak. That means you take the derivative and equate it to 0. So that's going to be d log f of x comma theta by d theta. At theta equal to theta hat ml will be 0. Right, that's the condition for ML estimator. So if you put the condition for ML estimator here, look what happens. So if I put this theta equal to theta hat ML, obviously this becomes 0 and this becomes theta hat ML, right? Because it becomes equal to 0. So remember, you have two things going on. You have an efficient condition, efficient estimator condition, and the maximum likelihood estimator. So this is the condition for maximum likelihood. So when you have an efficient estimator, if you see that if you bring in the maximum likelihood estimator condition, then read the right side. So if you can show that this quantity is not 0, then this quantity must be 0. That means, provided A is not 0, then that means Tx of x is theta hat ML. That means your efficient estimator is also, so I have proved another theorem. It says that efficient estimator is also the maximum likelihood estimator. That's what it is telling you. Look at here. When you have this efficiency condition, if you impose the maximum likelihood estimator condition, then this is your efficient estimator. And it turns out to be actually, so when you have things going well for you, a lot of things are going well for you. So the efficient estimator is also maximum. I am not saying all maximum likelihood estimators are efficient. That's not what I am saying. I am saying that if you find an efficient estimator, then it is also the maximum likelihood. Remember, maximum likelihood estimators doesn't even have to be unbiased. They don't have to be efficient. But if an efficient estimator exists, we just showed that it will be also a maximum likelihood estimator. This is so the final thing only I have to show is that, let me show you that A is not 0. Okay, so let me go back to this expression that we had. So we had the condition for efficiency was, what was it? D log f of x comma theta d theta is a theta tx minus theta. This is the condition for efficiency, right? So let me take the derivative on both the sides. So this gives me d squared log f of x comma theta d theta squared. From here, look at here, it's going to be the derivative of a multiplied by tx minus theta plus a multiplied by the derivative of this quantity with respect to theta. So that's going to be minus 1. Now let me take the expected value here. So expected value here is expected value is only on this quantity. So expected value of this, and the expected value of this is constant. What is the expected value of this? Expected value of tx minus theta. Because expected value of tx is 0. I mean theta, so this is 0. So you get a of theta is, you get the expression a of theta is minus expected value of the second derivative of log of f of x comma theta d theta squared. But somewhere, look at here, the second derivative is positive. The second derivative is the same as expected value of square of the first derivative. So that's positive, it cannot be 0. So this quantity is not 0, we just show all this is true. Look at here, this second derivative is the negative, or either way, the second derivative is negative of the second derivative is the square of this quantity. So this quantity is positive. So the negative of the second derivative is positive. Negative of the second derivative is square of the first derivative. What is the difficulty? Something. Everybody is clear with this?
So why is there a strict equality?
Okay. So you can see here, if this quantity goes to 0, then this will blow up, right? The variance is, then the bound is in fact meaningless, right? So for things to be meaningful, this quantity need to be positive, right? And so when will it, so that's the, so this quantity is also, we will discuss this, is also known as the Fisher information contained in the density function about the theta. So either this or this, and especially I'll talk about this when we talk about more than one parameter, multiple parameters. So to summarize, all the unbiased estimators, variance are bound by 1 over the expected value of the square of the first derivative of the logarithm of the density function, or minus of the second derivative of the expected value, inverse of that. And you can have cases where the variance is equal to the bound, in which case you get efficiency, or you call such an estimator to be efficient, the best estimator. So it's unbiased and the lowest possible variance. But then we see that when that happens, you don't have to check. Another byproduct is that estimator is also a maximum likelihood, is also the maximum likelihood estimator. So that's nice to know. So you have that, so you can see the power of maximum likelihood. When things are going good for you, then that pops up. It's also the maximum. I'm certainly not saying all maximum likelihood estimators are efficient. I'm saying the other way. All efficient estimators are also maximum likelihood estimators. And